Hey, so let's go over what we did over here in CalcPlot. So if you look at this, I forgot to mention that they wanted to show that this is always unstable. Well, look, if this has to be unstable, meaning if it has to be on the right side of this graph, then mu has to be greater than -1. So we can't really say that it's always unstable, but we can say that the spiral will always be unstable because in order to be a spiral, we need to be between -1 and 3, and definitely will satisfy this first condition. However, if we get above 3, we might not even get a spiral. So I can't say I'm super happy about the wording of this exercise unless there's something that I'm not understanding. And in that case, I would really love for someone to tell me in the comments. But as of right now, what I'm getting at is that there are certain mu's that will get this to unstable saddle point or unstable spiral, but I don't see how this will always be the case. But let's look at this. So let's pull down in CalcPlot a vector field. So that's going to be over here. And we're going to ask it to display the differential equations notations. And here we're going to use m for mu, so mx plus y, and minus x plus y here. So minus x plus y right here. We're going to have 0 for the third equation because we don't have any, and that's going to allow us to display everything in a plane. And then if we hit this, it'll display it for us. It looks pretty cool, just like that. And look, at where we are for m, which is, oh, by the way, between these two, we get a spiral, and it's unstable. If I click on any point, I get away from that spiral. Look at how cool this is. I get away from that point. I never get to 0. I can, if I start at 0, I'll stay at 0, but anywhere close to that, I'll never get closer. I'll just move away. Sorry. I'll just move away as time goes on. See? I can make this, for example, make it 30, and if you animate it, the time, it's just going to go away. It's just going to go away. It's just going to go away. And now, let me show you that if we get a mu less than -1, so that's going to be right here. Let's put like -1.1. Well, doesn't this look like a saddle? Because I am approaching 0, but look at what we are getting. And it'll be more obvious if we make this like this. And at this point, to make it easier to look at, we use fixed length for the vectors. We want more vectors. So let's say we want 14 vectors like that. Now look at this. Now, doesn't this start to look like a saddle? We can even make it -3, and it starts to look like a saddle even more, right? So notice how there's this vector that we approach, and we should be able to find another one. And that is this one right here, which on the other side would be this one. One of them is going to be, see, I found it. One of them is going to be, because you remember how this can be solved, and we can find 2 lambda values. And once we find the 2 lambda values, we can write the solution, and we're going to have a first vector times e to the lambda t, and a second vector plus a second vector times e to the lambda t with some constants in front. And what these vectors are, one of them is going to be the vector that you approach as you go to infinity faster than the other, because the lambda on one is going to be faster than the other. And the other one is going to be the vector that you approach if the constant in front of the other is 0. I'll try to make a video of that. I think I made one earlier, but I'll try to make a video where I explain it all out in detail. And I hope this was useful. So I think this validated our observations that, hey, can this only be unstable? Well, let's see. Can this only be unstable? This is unstable. This is a spiral, which is unstable. And this is still unstable. And I wonder if we go above the 3, so let's say we go to 4, is it unstable? Well, yes, it's still unstable. So it looks like there's something in our analysis that wasn't completely right. 7, see, now it just keeps getting unstable. So it's always unstable. So let's try to understand. So to be always unstable, this means that the tau, at least from my understanding here, it looks like it'll always be, if tau is negative, it should be stable. But apparently that is not the case, because we set this condition and we're saying if mu is greater than -1, well, in all of these cases, mu is greater than -1. So all of these is unstable. Well, what about if mu is less than -1? I really hope my analysis is true. All right, so let's see. What if it's, well, this is -2. And it looks like, in this case, is unstable because it's a saddle. So this is what they're saying. Oh, I see it, I see it. I hope you see it too. See, here we said, hey, if we consider that a saddle is unstable because you can't really get to 0 very easily, see? It always goes away. If we consider that a saddle is unstable, and it's going to be a saddle for mu less than -1, and it's going to be a spiral unstable for any mu greater than -1, and we know it's going to be unstable it's going to be unstable for anything greater than this, then this, yes, is a subcategory of the spiral, but it's always going to be unstable. And so now I see it. That's pretty satisfying. And I'll just leave you with this to show you how cool math can be. And I hope you don't mind that the previous video said some stuff that I guess wasn't completely the right interpretation, but you see how math understanding works. You may have an idea, you may have an intuition, and that intuition might be wrong, and that's okay. That's okay, as long as you recognize it and you recognize why it was wrong. And I recognize that it was wrong because I didn't catch that this was a subcategory, and then that these essentially make everything span the whole number line except for -1. So I wonder what happens at -1. So if we go to -1, oh, this is the limit case. And I think this is an interesting case to look at. I still don't know exactly what eigenvalues this comes from, but I think it's super cool. I think if we go over here, well, if that is -1, then all of this is 0. And if all of this is 0, we're on this. We're a degenerate stable node. So that's the only one on the number line that makes this stable. Everything else, unstable. All right, this was pretty cool. I hope you found this interesting, and I'll see you next time.